In this lecture, we're going to talk about a topic you probably never heard of. This is engineering psychology. It's one of a number of applied fields in psychology. So far, we've talked about what is pretty much classic academic psychology. But psychologists, when they come out of a psychology program, often don't go into the academic world, but they go into an applied setting. And they have to do things that help people solve problems. And they may go into different kinds of settings. They may go into a setting that an industrial organizational psychologist might go into and help people select employees, figure out how to compensate employees, perhaps how to set up the corporate structure so that it's most productive. That's what those kinds of folks would do. But there are other folks who go into settings where they try to make people compatible with machines and with environments and with certain processes that go on in that industry. And those people are called engineering psychologists. What we want to do today is introduce the field to you a little bit and talk a little bit about its history and its relationship to other fields. We want to talk about the basic idea of allocating tasks to humans or to machines. And we want to talk some about, just give you a sample of design recommendations that an engineering psychologist might be able to make. As I say, this is probably a new concept to you, but I'm an engineering psychologist. I was actually trained as an engineering psychologist, and it's not a new field. I'll talk to you a little bit about the history of it. I got my PhD in engineering psychology 36 years ago, so it's been around for a while, although it has changed some over the years. When I tell people I'm an engineering psychologist, that usually starts a good conversation. Most of them think I'm psychoanalyzing engineers at that point. I don't psychoanalyze engineers, although some of them need it. But in fact, what I do is work in engineering psychology, and I do what other engineering psychologists do. We're interested in considering the human as an engineering component in a human-machine environment system. Engineers specify what the other design components, the machine components, can do in this system. What engineering psychologists do in much the same manner is say, what does the human operator look like as a component in this system? Let me give you a little bit about the history of the field. Prior to the Industrial Revolution in the early 1900s, prior to it getting started, people designed a lot of their own tools and designed a lot of their own devices. So if you're walking through the woods and want a walking stick, you find a nice stick and break it off, approximately the good length for you, and use it as a walking stick. And even in industries where they did have engineers, usually the engineers took their best guess about what the human was like. So if they're designing a shovel, let's say, to shovel gravel, they know that that shovel head should probably be smaller for gravel than it is for sawdust, where they might make a larger headed shovel. And that seems to be somewhat common sense. Unfortunately, a lot of engineers even today think that this field is common sense and that they can go ahead and do it without the help of psychologists. However, during World War II, they kind of came to their senses because engineers got very good. And they started designing very complex systems like high-speed aircraft. And those complex systems usually worked great. But every now and then they'd have a problem, like the aircraft would fly into the ground or into the side of a mountain. And then they would do an accident investigation and put the aircraft back together, trying to figure out what went wrong. And they might discover that it wasn't one of the physical properties of the aircraft. The wing didn't suddenly fly off or something like that. But in fact, they called it pilot error or operator error. Unfortunately, that didn't explain very much and didn't tell them how they might design the system any better. They had designed the system so that it was beyond the limitations and capabilities of the human operator of the system. They did it because they didn't know what the design characteristics of the operator were. And so at this point, they had a problem. And they first tried to solve the problem through selection and training. So you can go in there and you say, well, the problem is we didn't have talented enough pilots. So let's put some tests together and select better people to be pilots. And then on top of that, let's also train them to be better pilots. So we'll get aircraft simulators and that sort of thing and train them to be really good pilots. That helps some, but it still doesn't solve the problem if you design the system so that it requires 2 heads and 4 arms to fly the system. Nobody has that. You can't find any pilots or train pilots to be that way. So then they had to come to psychologists and say, tell us about the human. And that's what they did shortly after World War II when they were experiencing these kinds of problems. They came to psychologists and said, you guys are supposed to know something about humans. Tell us what the human operator is like. Unfortunately, psychologists didn't have very good answers at that point either. They had been in laboratories running mice and rats in their mazes and studying nonsense syllables and people's memory for nonsense syllables. They didn't know much practical in terms of what the human looked like as a design component in this system. And so psychologists decided that some of them said, this is an interesting and perhaps a lucrative thing to do. Let's see if we can find something out about humans and the way they operate in systems. And that's where the field of engineering psychology was born. And it has, through the years, grown. When I was being trained as an engineering psychologist, most engineering psychologists worked in military settings. Because of this early history, a lot of the complex machines were being designed for the military, and the military was a large enough organization that they could see across all of these machines the kinds of common problems they were having. And so they hired a number of engineering psychologists at that point. Going up in history, in history in terms of years, beyond the military, an interesting thing happened in the 1960s and 1970s, and that's computerized systems. At that point, when you could design some intelligence into a machine, whether it be a personal computer, or whether it be an automobile, or whether it be a spacecraft, and you have some computerized system that can be intelligent, then you say, how can this intelligence be compatible with the human intelligence? What should we give the machine to do? What should we give the human to do? And how do we make these compatible? And that's a very interesting question, and cognitive psychologists have some answers for those kinds of questions. So if you look at the growth of the Human Factors and Ergonomics Society, and I'll talk about those terms in just a minute, that's the professional society that engineering psychologists are in. There was some steady but slow growth in the 1950s and 60s, and then you see it really take off. And it goes from 500 members up to 4,000 members in about a decade or two. And most of that growth was in consumer industries. And for the most part, these were in computerized systems. And that's where most of the students we train in my program go nowadays. They go to the large industries that design computers and computerized systems. So that's been a large recent growth in the field. Let me try to characterize the field a little bit in some other terms that you may be a bit more familiar with. In your course guide, there's a figure that I drew for you that is in the shape of a square, and then it's divided into 4 quadrants. Those quadrants represent sort of the academic fields that contribute to the entire field that we're talking about here. In psychology, that's one of the quadrants. Another quadrant is engineering. Another quadrant is physiology. And the 4th quadrant I labeled others and includes such things as anthropology, geology, sociology, archaeology, and rather architecture. And those fields also interact in terms of designing things for people. So those are the 4 fields that are your traditional fields. Then in the middle I have a shaded area which represents human factors or ergonomics. Those are 2 terms that have been used for the interdisciplinary part of to describe somebody who does this kind of work. The older term, human factors, was used for a long time. Today, more often we use ergonomics. Our program in my university that trains engineering psychologists is called ergonomics, And we have a sister program over in industrial engineering that's also called ergonomics. So that's kind of the interdisciplinary term. And where it overlaps psychology, those folks are typically called engineering psychologists. And where it overlaps industrial engineering, those folks are often called human factors engineers. In Europe, ergonomics is fairly big, and there they have quite a few physiologists who are also doing this kind of work and studying work physiology. And then it does overlap some of these other areas as well. So that's the general field and some of the terms that are used to talk about the general field. One of the first questions to ask in the design of systems is, what should you give to the human and what should you give to the machine? How do you allocate your tasks? And in order to illustrate this, I also have a figure in your course booklet that gives kind of my conception of how this works. And what we have is at the top of the figure we have human, and at the bottom of the figure we have machine. And then it forms kind of a circle as you go around the figure. On the machine side you have controls that people use, be it a steering wheel, a lever, a keyboard. And then you go into machine dynamics. If it's a computerized system, it would be the kind of hardware and software that's in the system. If it's a vehicle, it might have to do with the particular vehicle dynamics of that machine. And then you have a display of some sort. The information coming from the machine has to be displayed to the human. So that's kind of the machine side of the thing. But that then leads in this circle up to sensory systems. We're now on the human side, so we're talking about the eyes, the ears, the sense of touch, that sort of thing, where you're getting the information from the display, and that information has to go into the human. And then on the human side, beyond the sensory systems, this information has to be processed cognitively in some way. So it goes to the brain, and we do certain kinds of things to process this information. And then once it's processed, it goes to a controller of some sort on the human side. That would be our hands, our feet, our voice perhaps even, in interacting with the machine. And then we're back onto the control side of the machine. So we've kind of gone around in a circle, and I think that's a good way to envision what goes on. We also have to remember that this entire circle is in a particular environment, and sometimes environmental considerations are very important, particularly in areas like space exploration, where you're in unusual environments, and you may have to design the system depending upon what that particular environment is. If you're going to allocate tasks to the human side of this circle or to the machine side of this circle, it would be important to know what machines are particularly good at and what humans are particularly good at. Machines are good for a lot of different kinds of things. For example, high-speed kinds of things. If you have a sorting task and you're trying to sort lots of things, if you're trying to sort the mail, for example, machines have pretty well replaced humans in that task because they're much faster. Humans only deal with the mail that there's some question about and that they have to use some judgment in that task. Machines are good for repetitive tasks and tasks that are dangerous. So you might want to send a machine in to defuse a bomb if you can, for example. Machines are good for tasks that require great strength. If I'm digging a swimming pool in my backyard, I'd sure rather have a backhoe do that than me and my shovel do that task. But humans are good for a lot of things too. Engineers sometimes think that the machine is the end all if they can do it. They want to automate everything. But in fact, humans do have some characteristics that are good in a human-machine system as well. Humans are good for doing unstructured kinds of tasks, things that haven't quite been planned for. In the space program, initially, in sending something to the moon, for example, the engineers wanted to send just a machine to the moon. And they were probably right. It probably would have been a lot cheaper to do it. But the president had said, we're sending a man to the moon, and so they had to build these very expensive and heavy biological support systems for the man to get the man to the moon. But the men on those missions often saved the mission because something would go wrong, and the human would sit there and try to figure out what went wrong and tape a couple of things together and make it work. and make the mission work, because the engineers couldn't have designed it so that they were sure of everything that was going to happen. Human judgment was sometimes necessary in this unstructured situation. Humans bring flexibility to the situation and their judgment and decision-making ability as well. When I was in graduate school, I worked on what was called a command control decision-making project. At the time, it was the Cold War was on, and we wanted to see whether we could aid people in making the decision about whether or not this country was at war with other countries, and which countries we were likely to be at war with. And there was a lot of information coming in from various sensory apparatus, from spies and that sort of thing. And the question is, how do you aggregate all of these probabilities and come up with a single decision, are we at war or not, with these various kinds of countries? And we discovered that we could use machines to help people make these decisions. You can use a theorem called Bayes' theorem to help you aggregate these probabilities and come up with a final probability. But in the end, they never wanted to trust the machine, and I might say rightly so, to make the decision about whether or not we're at war. The human was always on the end of that system because they knew humans could bring their own judgment to bear, and humans are particularly good at doing those kinds of tasks. All right, so here we know what humans are good for and what machines are good for. But engineering psychologists go beyond that, and they have certain kinds of design recommendations that they make. We have handbooks of these kinds of things, and I just want to give you a little sample of this. Let's take the case of trying to display quantitative information for somebody on a display. And how should you display that quantitative information? Well, it turns out it depends on what you want to use that quantitative information for. We get quantitative information for a number of reasons. For one thing, we might want to do a check reading. That is, are we where we ought to be at this point? That kind of reading. Or we can do it because we want to set something at a particular level. That would be another task that you might want to do. You might want to do tracking. So you're doing something, trying to follow this quantitative reading around and trying to track it in some way. For these different kinds of tasks, you might want to have different kinds of displays. Let's take, for example, a display that has a dial that's fixed and you have a moving pointer on it. Now that sounds complicated, but what I'm really talking about is something like the watch that you wear, where you have a watch with a fixed dial and you have a moving pointer on it. And the design recommendation there is that that's a pretty good display overall. It's particularly good for check reading, for saying about what time is it, for setting something, and for tracking something. And let's compare that with a digital display. A digital display would be like a counter or something that you're reading out numbers on a particular display. Digital displays are good for quantitative readings, and they're good for setting tasks, but they're rather poor for check reading tasks. And I knew that back when I bought a digital watch for the first time. When they had just invented digital watches, sounded like a good idea to me. They were cheap. I went out and bought one, had a little stopwatch function on it and that sort of thing, strapped that on, and I said, boy, I'm never going to use the other kind of watch again. But then I quickly discovered that digital watches didn't quite do it for me. The first time I was expected at an 11 o'clock meeting, looked down and said, oh, well, it's only 10:58. I have time before that 11 o'clock meeting. And then realized I had to actually subtract something from something else to see whether I was getting close to 11 o'clock. I discovered it would have been much easier to look down and see that the dial was, or that the pointer there was, oh, it's almost 11 o'clock. I don't have to subtract and say, well, it's 2 minutes away. It's almost time. That's what I use my watch for most of the time, sort of as a check reading. Is it about this time? And I've gone back now to an analog watch. I don't use a digital watch anymore. Did have some good things about it. At that time I was a runner and wanted to know my running times, and it was important to get it to the second. And so I would set my stopwatch and start it and stop it. It was good for that. I like to cook, and I would cook certain kinds of things and again set my stopwatch for, well, that ought to be in there for 4 minutes before I take it out. It was good for that sort of thing, but not for what I usually used my watch for. And so those kinds of display considerations, you can see why they're important. When speedometers switched over to digital shortly after digital came out and told you were going 67 miles an hour, people said, isn't that great? I can tell exactly how fast I'm going. But then again, they discovered that's not what they wanted to do. They typically either wanted to do a check reading. Am I going about the right speed here? I don't want to subtract there either. Or they were doing a tracking task. They were trying to use the accelerator to track the speed of the car, and doing this and using a pointer, a moving pointer, is better for that kind of task. There are displays that use fixed pointers where the display itself moves. And those are particularly bad displays for almost everything. And in your course guide, I have an example of that, which is a kind of display and a control at the same time. It's a knob that, like you might find on the side of a heater, let's say a room heater, where you want to have it either hotter or cooler, and so it goes high or low. And you have this knob with a fixed pointer. So the pointer itself is on the body of the heater, and the knob you can turn, so you're kind of turning the display itself. And on this knob, on one side it says high, and on the other side it says low. And there's an arrow going clockwise and an arrow going counterclockwise. And if you look at that in your course guide, I think you'll find it very difficult to figure out which way you ought to turn the knob in order to turn it higher or to turn it lower. And in this case, the engineer doesn't even have a case to be made that it was easier to design this way, because using the same knob and the same body of the machine, you could redesign it so that the pointer is instead on the knob rather than on the body of the machine. And then on the body of the machine have your scale of going from low to high, and then it becomes very obvious which way to turn the knob simply by changing the display. Let me give you one other example. Even when you have a fixed or a moving pointer, you can have problems with reading the display. Again, in your course guide, there's a display that looks like the display on your electric meter on your house. And it reads kilowatts and kilowatt hours. And there are really 4 separate dial faces on here and 4 separate little pointers on it. And the job of the meter reader is to read each of those and figure out what the 4-digit number to say how much you have used in terms of kilowatt hours. But it violates a number of different kinds of principles, because it was designed by an engineer who was trying to save money and save a couple of gears, which probably saved the company millions of dollars, because they make many millions of these machines. And so it's designed in some cases with overlapping kinds of dial faces. And almost all of them have clockwise goes up on one of the faces and counterclockwise goes up on the other face. And when you try to read this, it's extremely difficult to do. They tried doing this during the Second World War and having people read their own meters, because they didn't have enough people to read the meters, and people were terrible at this. They ended up having to actually send out postcards with the meter face that just draw the pointer in where it is, we'll read your meter for you, because people were particularly bad at doing this kind of thing. So displays is one place where you can make recommendations like this. I wanted to introduce the concept of population stereotypes as well. With population stereotypes, we're talking about tendencies built up in certain populations for linkages between a particular action and a particular result. Let me give you an example of that. Most of us, in order to turn something on, will flip a switch up. That's a population stereotype that we have. And it usually works. In our houses, sometimes if you have multiple switches in a room, it doesn't quite work that way. But for a single piece of equipment you buy, if you want to turn it on, you generally flip a switch up, and that works pretty well. I had a sabbatical in Australia a number of years ago, about 20 years ago, And I was surprised when I went there that not all of their switches work the way our switches do. They have 220-volt current instead of 110-volt current. And for that reason, they have more switches on things like what they call their power plugs, or their power points, which are plugs, what we call an outlet in a wall. And next to the outlet, they'll often have a little switch on there. And they use a switch as a rocker switch instead of the switch we're used to. And to turn this rocker switch on, you actually push it down. And what that does is expose a little red dot on the top of the switch, so you can look over at the outlet and see whether the outlet is on. If the red dot is there, then the outlet is on. And so they use this not only for their outlets, they use it for their room switches and that sort of thing. So in Australia, you kind of flip something down instead of something up, and it took some getting used to because that's an opposite population stereotype than I was used to. Typical population stereotypes are knobs that should be rotated clockwise in order to move something up or to the right. If you have a lever instead of a knob, you generally move the lever up to move something up or to the right. Those are additional population stereotypes. Now, just because engineering psychologists make recommendations, people don't always follow those. There's a study that was done a couple of decades ago where they were studying stoves and how you arrange the burners on stoves, the 4 burners, with the knobs on the front of the stove. The 4 burners are usually arranged in kind of a square design, and you have the 4 knobs going horizontally across the front of the stove. Which knob should turn on which burner? So they studied this a bit, and they would do an experiment where they would put up a mock-up of a stove with this arrangement, and they say, okay, I want you to turn on this burner, which knob would you grab? And so they studied people and the kinds of errors they made in this situation, discovered that the best way to design the stove was to actually offset the burners. So rather than being in a square configuration, they were kind of in a parallelogram configuration, and then it became quite clear which knobs worked which burners. And so in this configuration, people made no errors compared to the more standard kind of arrangements where they made anywhere from 76 to 129 errors in this particular study. So one might think, well, now we've discovered how to do this kind of thing. All the manufacturers will see the beauty of what we've done and will build their stoves that way. Well, going 15 years later, they went back and looked at stoves to see how many were designed this way with the recommendation, and in fact, none of them were designed that way. They essentially ignored this. Now, to be fair, these engineers have other things to consider as well. To design a stove this way makes the stove a little bit wider, and if the stove's a little bit wider, it doesn't fit into the hole that building designers leave to stick stoves in. So there are a number of other considerations as well. Nevertheless, it is a frustration of people who work in engineering psychology that often they do all this work and people end up ignoring them. And part of the reason is that people don't even realize that this field is out there to help them with their products. That's part of the reason I'm lecturing on it today. So you at least will realize that this field is out there. Now, not all engineering psychologists do what I call neck-up work. That's cognitive engineering psychology. There are other fields in engineering psychology as well, although neck-down work is more often done by industrial engineers than it is engineering psychologists. But some psychologists do that. Neck-down work is the kind of work you would do if you're designing a particular space, let's say. You're sitting in your car. Can you reach the radio? Can you figure out how to work your windshield wipers? Those kinds of questions. Can you reach it? Can you use proper strength to activate the kind of thing? So design of space, design of even clothing. They do work with it's called they do work that has to do with measuring people to see what their stature's like. Try to design a car so that people can reach the pedals. Between the 95th percentile perhaps and the 5th percentile people can all reach the pedals and that sort of thing. So that's kind of neck down work, and some of that goes on in engineering psychology as well. So what I've tried to do today is just give you a quick overview of engineering psychology, give you a little bit of the history of the field and how it relates to other fields, give you sort of an overall definition of this, and then lead you through just a couple of considerations in terms of what tasks you ought to assign to humans and what tasks to the machine, and also some simplistic notions of design recommendations to give you just a quick overview of the field. Thank you.